Okay, so we're back for 522, and this is part 2 on November 5. Okay, so before the break, we talked about this idea of rotation, and we said that this is related to the idea of introducing a transformation matrix. Okay, so remember, there's our transformation matrix, and we said that one thing of factor analysis, where it can come under some critique, is that if you introduce that transformation matrix, you can still regenerate that correlation or covariance matrix. Okay. So the idea of rotation then has to have a different purpose, than getting a better approximation to this. That's the main idea. Let me just repeat that because it's an important point, is that the idea of rotation isn't to reproduce this. Okay, the idea of rotation isn't to say, hey, let's get a better reproduction of the covariance matrix. That's not the purpose of rotation, because the rotation is going to just as well reproduce this because of that idea of introducing a transformation matrix. Introducing the transformation matrix, remember, had the idea of still satisfying the factor solution. So that's not going to be the reason for it. The reason for it is going to have to be something else, and it's going to provide better interpretability. Okay, provide better interpretability, because when you do the original factor analysis, it's not done to provide maximum interpretability. When you transform the factors using the rotation, there's that transformation matrix T. This book doesn't go into those equations that we talked about, but when you introduce that transformation T, it often provides a much better improvement in terms of interpretability. So that's very, very key, is to understand why you might want to do a rotation. Now, there's a couple versions of rotation. Well, there's actually many, many different versions of rotation. Okay, rotation these are just a couple options that we're going to look at. We're going to look at Varimax and Cordimax. But there's many different versions. And if you really get into factor analysis, if you're looking at factor analysis here and you're saying this is going to be my thing, and you want to study it further and do factor analysis for people and stuff like that, you're going to come across different rotations. We have one student who's actually doing quite a few factor analyses and things like that. So you end up almost like specializing, and you look at some researchers who, that's what they do, is they do factor analysis, and then you're getting into like many big books and stuff like that, and you're specializing in the different rotation methods. If you want a good author on factor analysis, if ever you really want to dig into it in depth, it's Stan Mulayek. Stan Mulayek wrote a book in 1972, which is a pretty technical book, but it's really well written, and it contains a lot of details on factor analysis, and it's like 300-400 pages. Just show you the vastness of the subject. There's two types of rotations here that Stevens talks about. One is the orthogonal, sometimes called the rigid rotation. Now, when you do the orthogonal rotation, the factors remain uncorrelated, as were the initial obtained factors, because the initial obtained factors are uncorrelated. The rigid rotation keeps them uncorrelated. The oblique rotation allows them to be correlated. So it's important also to realize too, what's being rotated. Okay, when you do the factor analysis, you do a rotation. First of all, you're doing it to improve the interpretability. So we have to look at how these are going to actually improve interpretability, because that's got to be the purpose for it. It's not to better reproduce this, because it's not going to better reproduce this. It's going to improve the interpretability. Okay. And again, that's the idea, is you can get a transformation matrix and reproduce this, but you don't need this to reproduce this. You can just go with the original reproduction. So the question is which reproduction of the covariance matrix or correlation matrix is going to be the one adopted? And that has to be based on subjective interpretability. So if we look here, there's that's an outtake from some other notes. This is the loadings matrix that's been transformed, it's got a star. This is the original loading matrix. So regardless of how you're transforming, whether you're doing orthogonal, whether you're doing oblique, this is the transformation matrix that you're getting. You're getting a transformation matrix. But they're both equivalent from the mathematical point of view. What does that mean? They're both equivalent from the mathematical point of view because of this idea, which we've surveyed. That's what that means in terms of they're both equivalent. You introduce the transformation, as we saw in our equations just above and previously, you're going to still be able to establish the covariance matrix or correlation matrix. However, they may not be from the psychological point of view. And by that, we're saying in terms of interpretability. So the problem of choosing one particular psychologically meaningful out of the infinite set has been called the problem of rotation. But the problem of transformation would actually be better, since it includes also the transformation to oblique factors, in which case the transformation matrix T is not orthogonal and hence does not represent only a rotation. So you can think of that in terms of when you do the transformation, you're doing it for the reason of getting better interpretability, and we'll talk about how these things work. Now, one thing to point out is when you do a transformation, say that's x1 and x2, just for demonstration here, I'm not going to go into higher dimensions. I'm just going to choose x1 and x2, so it's not going to be an exact representation here. But realize that when you're doing the transformation, what you're really transforming are the loadings, because I'm going to have F1 and I'm going to have F2. And what does PCA do? PCA, there's my original variable. I'm transforming by getting loadings on that eigenvector. That's the transformation that's taking place. When I have the F1 and F2, when we issue a transformation, these loadings are going to be transformed. So remember that in this respect, there's some similarity between components analysis and EFA, because when we conduct the transformation in PCA, we have observed variables, but what is the transformation that's taking place? What's the transformation? The transformation that we obtain is a components analysis. Y is equal to AX1 plus, etc. So really, we're getting these particular loadings, there's A2, etc. Whereas what were these loadings before the transformation? These loadings before the transformation were what? Equal to 1. They were scalars of 1 before the transformation. After the PCA orthogonalization, transformation is how I'm using the word, we're obtaining different loadings. Realize that variable x1 and variable x2 are still there. I didn't actually transform x1 and x2. Okay, I didn't actually take x1 and say, I'm going to change you. Right? So if you want to look at the components analysis with, like, say, just verbal and quantitative, I didn't transform V. I didn't transform Q. What I did was weight them by different scalars other than original scalars, which we may say is just equal to 1 if we had to pick something. That's why I put the 1 here. That's analogous to what happens in factor analysis, because in factor analysis, when we transform, when we say, we're going to transform the factors, what we're actually doing is just selecting different loadings. We're transforming things so that the loadings change. Only in the case of factor analysis, that transformation becomes even a little bit more weird, because these are unobserved variables. Right? These are unobserved to begin with. Now we're transforming things here on the unobserved variables. Okay, so things are really getting like, what is going on? Look at incomponents analysis. We do a transformation and eigenanalysis, and then we weight the x1 and x2 based on that transformation. x1 and x2 are x1 and x2. I'm not changing x1 and x2. I'm just weighting them differently and then getting my component. Look at everything that's going on in EFA. EFA, that's why we say EFA is like, wow, a whole bunch of stuff is going on, because these are not x1 and x2. These are unidentified factors. They are latent variables. So not only is the factor analysis, the original factor analysis, generating factors, but now you're going to transform via rotation, via T, via transformation matrix, you're going to transform the loadings on the factors. So you're loading these differently. So you're loading things, here's the summary, right? You're loading things that don't naturally exist based on some kind of a rotation. Whereas in the PCA, you're transforming things that are measured, observed variables that, you know, we could say do exist in this sense. Again, you get into the measurement problem, and we're not going to go into that again because we could develop that for say, well, you know, remember we talked about weight and height and all that stuff. We're not going to go there again, but you get the idea. You get the idea. This becomes almost like, that's why we say factor analysis is a latent variable procedure, because so many of things, it's like you're going to transform what? You're going to transform the loadings on what? On hypothetical variables. And not only that, but you're going to be able to select a whole bunch of different transformations on those hypothetical variables such that they maximize some quantity that you want to get for interpretability, which is, it's going to be like maximizing interpretability. So again, big picture, PCA, relatively atheoretical, not too many options really. It does the when you do a PCA, you already are doing a transformation. You know, when you do this, you're transforming to components. But look at all the, you know, if you want to think about this from a hard scientific point of view, is look at all the rigor, right? You got X1, X2 transformation. You get, you know, the PCA1 is PCA1. It doesn't depend on 2 and 3, etc. Whereas here, a whole bunch of stuff is going on. So that's just really important. Now, you're not going to hear about that when you do the factor analysis or when you read about it in the literature. They're not going to go into these issues, because you'd have to talk about them every time. You need to be aware of them so you know what you're interpreting. Nothing worse than interpreting something that you think is, oh, I found 2 factors, period. No, wait a minute. Lots of stuff to know what went into the mixing bowl, right? Like the cake tastes great, but you're not just interested in the taste of the cake. You want to understand what went into this so you can critically evaluate it for yourself so you know what's there. The measurement problem, right? A lot of this is related to the measurement issue of the factors. How do we know there's 1? How do we know there's 2? And further, can you name those factors? Now, I've talked a lot about the measurement issue because it's really, really important. And if you want an example of the measurement issue, and what I mean by the measurement issue is before you analyze something, maybe that your contribution should be, what are we analyzing? Oftentimes data is subjected to analysis. You get the analysis, but you're building on the foundation of X1, X2, X3, these measured variables. So, I think more attention needs to be paid to what are we measuring in the first place. Maybe that's the psychometric study that should actually be conducted and get a better measurement of it. I mentioned it before the break. Maybe you want to measure mindfulness. You want to use does mindfulness predict success? Just as make up an example, does it predict future success? Wait a minute, ask yourself, what is mindfulness? And maybe you'll even stop there. And after you do a little bit of research into what mindfulness is and where the construct actually came from, maybe that'll stop you and you'll say, I'm going to examine, does mindfulness actually exist? And is it related to something else? Before you just assume it exists. More attention to the measurement problem. Do we need a better example? Do we need a better example given what was just happened 2 days ago? It repeated itself 4 years ago in terms of why is the measurement problem important? Why? Because in Wisconsin, they said there's going to be a 16-point difference between Trump and Biden. I think it was 16, and I think it was Wisconsin. But they said there was going to be a 16-point difference. What was the actual difference? It was like 1%. The actual data was a 1% difference. The hypothesis that they came up with was 16% difference between that. That's all about measurement. It's not about analyzing the data or computing z-tests and z-tests and stuff like that. It's about what are we measuring in the first place. And that's why it's so important, because they're obviously not measuring what they thought they were measuring, you know, when they asked the person who you're going to vote for, or, you know, and I'm assuming that their sampling procedures are correct. There's no reason to doubt that the sampling procedures wouldn't be correct. If it's a reputable polling company, they're going to know how to randomly select, maybe stratify the sample a little bit so they get a little bit of each demographic group and all that stuff. So we have to assume they're doing that right. But clearly it went completely wrong with the polling, because it means they're not measuring this person who goes Biden. They are not measuring that. They're measuring something else out of the many things they could be measuring. So what, you know, if you look at that and you say, what were they actually measuring? Maybe they were measuring something called a verbal report. And the verbal report was Biden. But that did not reflect, this is the person's head. I'm inside the person's head. It did not reflect whatever the heck was going on in here that generated this. So maybe the polling company needs to say, well, okay, you just said Biden. Now let me dig further and see if this is a corresponding representation of what we're actually trying to get at. And I cannot emphasize that enough. And the whole history of psychology is the measurement problem. And that's why when you sometimes hear of, you know, like say a chemist, and you're talking to the chemist, say, well, I'm going to do this, I'm going to do that. And the chemist may say, well, how do you even know what this stuff is? And it stops right there, right? It stops at, well, I don't know. Well, there's the measurement problem. How do you know self-esteem exists? What is self-esteem? What is depression a score in the BDI? How do we know? Think about that further. Maybe do some validation studies. Maybe reconsider what depression might be. All of those things are really, really important. Okay. You know, so we talked about the polling in terms of the measurement. Another example was like in Ohio, I think Trump came out like 8 points, and they had forecasted like Biden winning by 5. So like the split was huge, and it's not based on the statistical problem, because all the polling companies have people who know how to do statistics really well. It's the measurement problem. That's the real thing. Or they didn't weight things properly. So if you don't think that you're measuring this, then maybe you have to weight things differently. But that's because you're not measuring what you think you're measuring. So you have to disproportionately allocate the weights in your polling algorithm that accounts for the fact that you're not measuring the truth. You're measuring something else. You're measuring what the person's saying, which doesn't accord with the truth. So it can become a statistical issue. But again, if the polling company is not focused on the measurement problem, and they're saying, hey, do you like pizza? 7. Okay. Do you like pizza? 2. Okay, wait a minute. Does 7 mean you like pizza a lot more than 2? Or are you just saying you like pizza more because, I don't know, maybe you think that's what I want to hear or something like that? Okay, so really, really important. Okay, so oblique versus orthogonal. Orthogonal, they're allowed to correlate. In the oblique, what did I just say? Oblique, they're allowed to correlate. In orthogonal, they are not. Okay. So when you use an oblique solution, okay, so when you use the oblique, when you allow them to correlate, interpretation of the factors becomes a little bit more complicated. Even, you know, we need more complication in factor analysis. Like, it's not complicated enough. Now, when you do oblique solutions, it becomes more complicated. And the associations between variables are provided in 2 matrices. One is the factor pattern matrix. Okay, these here are sometimes called pattern coefficients, and these are analogous to standardized partial regression coefficients from multiple regression. A given coefficient indicates the unique importance of a factor to a variable holding constant the other factors in the model. And you also get a factor structure matrix, which is the structure coefficient. And these are the simple correlations of the variables with the factors. Now, which to interpret exactly is oftentimes a matter of choice. You might want to use a triangulation method in terms of what you're obtaining. But there's our structure coefficient idea. And you remember from the previous assignment, structure coefficients are simple bivariate correlations of the variables with the factors. And when you think of structure coefficients, well, they're ignoring that context, because the factor pattern matrix, holding constant all other factors in the model, provides a little bit more context than the structure coefficient. Okay. What coefficients? Well, triangulation should probably be used for those things. There's not necessarily, you can read what Stevens has to say about cutoffs and things like that. But kind of a triangulation. And again, you shouldn't be looking at those things and saying, well, I should interpret one matrix versus another, because we know that it's kind of exploratory. Factor analysis depends on so many different things that you don't want to get stuck on one thing. Rules of thumb in factor analysis, forget about them. Just use them as guidelines. It's much too exploratory. It's much too dependent on a whole bunch of things that you don't want to, like, it's not an exact recipe for that. Sample size and reliable factors. Here again, big samples. Big samples are best, but there's no rough guideline. Now, one of the distinguishing features here is depends on how many factors that you can actually expect to extract. So when you talk about minimal sample size requirements as related to communalities and the number of strong factor loadings, one thing to keep in mind is if you have strong evidence for factors, then you may not need that big of a sample size to get them out. And we'll talk about the nature of a communality here, but we say that the average communality is 0.70 or greater. Well, good estimates can be obtained with sample size as low as 100 and even lower. Again, rough guidelines. And the communality, we're going to see, as we talked about briefly last time, I think, how much variance is explained by the given observed variable over the factor solution. So if the communalities are pretty high, which indicates you have a pretty strong solution, then maybe you can get away with 100. But really, you should not be aiming for 100. If you're doing a factor analysis, you want to usually, to be safe, be nice to get it even in the 300 range, 400 range. And that's why sample size 200 or greater. I say a little bit greater. Communalities, you don't know what your communalities are going to be. That's one thing. You just don't know what they're going to be. Assume they're small and get them to 400 or higher. What you definitely don't want to be doing is doing factor analyses on 50 observations and extracting like 5 factors with low communalities and making all kinds of conclusions from that. Because that's not going to be very reliable. It's a large sample technique. More sample size is better. Which indicates another thing too, is when you're thinking about, should I do a factor analysis? Well, do you have sample size for it? Is it even feasible to get that sample size? And if you're doing a factor analysis based on like archival data, that's sometimes a nice thing to do, because maybe that archival data, you have 1,000 observations, or maybe you're doing it on COVID, things like that, and you have a database that is collected by a different organization that you can get permission for and run it on 3,000 observations or something. That's kind of nice. If you're doing it in terms of a thesis, well, maybe you can't get 300-400. So don't settle for something really less. Maybe consider a different technique, or whether, look in the literature. If there's strong evidence that you're going to get good factors, well, maybe then sample size of 100 to 200 is sufficient, but there's no strict guidelines here. Okay. The general idea, though, is if your commonalities are going to come out to be strong, then lesser sample size can be used than if they're going to come out to be weak. Okay, so obviously there's a surprise here, or just like that. Simple factor analyses using principal components extraction, like that. And at this point in the chapter, you're probably saying that with me, right? You're like, you can't believe it either, right? And it's not, there's nothing wrong with presenting it like this, as long as you know what's being presented, which is why I've kind of prepped us to see what this interpretation is. Well, it's a factor analysis using principal components extraction. Factor analysis using principal components extraction. So think about what that means and what we've talked about. Principal components extraction doesn't really mean the same thing as the factor analysis extraction, right? So right away we see that, and with everything we've talked about, these things are not the same. There's a lot going on here. And again, if you understand the issues we've talked about, then you read that sentence, you're like, yeah, I get it, I know. But if you don't know what we've talked about, or we haven't talked about that, then you look at this and you say, oh, so I guess you're just extracting components, and components analysis is the same as factor analysis. It could be very, very confusing. So mindfulness seems to be the word of the day. So please be mindful of what we've talked about in our previous stuff in this chapter for interpreting all of this, because this is the part of this chapter where the book is kind of equating the two and just saying, let's just say factor analysis is pretty much the same as principal components analysis. Because what they're talking about, what Myers is talking about here, is simple hypothetical factor analysis, but they're going to use components extraction. So it's not a factor analysis, it's a components analysis, but they're still talking about it in terms of a factor analysis. Okay. Tabachnik and Fidel will do the same thing if you ever use that book for reference and stuff like that. Principal components extraction with 3 items. So this is basic factor analysis demonstrates principles. Here's some 3 items. There's the bivariate correlation matrix. You got stimulate, challenge, and interest. And there's our correlations. Now, Bartlett's test here, you probably, you don't have to do it. You can do it if you want, but you look at this and say, hey, does that look like an identity matrix? And you say no, because there's correlations between variables. If it was an identity matrix, then that would be 0, that would be 0, 0, 0, 0, 0, and you would just have the ones here. So looking at that correlation matrix, you say, yeah, it looks like there's sufficient correlation to try the factor analysis. Again, what's your theory when you do the factor analysis? Well, you don't really have one, but at the same time, the reason why you're doing it is because you think that there's some underlying variable, latent variate, that subsumes these characteristics. Otherwise, there's really no sense in doing it. Now, that may seem a little bit familiar to what we talked about when we talked about a MANOVA. Y1, Y2, Y3. Why did you do the MANOVA? Well, you had some research reason for putting these together. That's not the same latent variable as you're going to get from this, but you had some reason for doing it. So right away, again, in MANOVA, what was one rationale for not doing MANOVA? One rationale for not doing MANOVA was not simply because you have more dependent variables at your leisure. This should be theory-based, and preferably, maybe you have an experimental manipulation here, which is even better. Here, the purpose of doing factor analysis is definitely not because you have correlation between variables. Because if these don't go together in some sense, or there's no underlying theory, then this is going to be so misleading that it's not really going to be interpretable. Murder rate, ice cream cone sales. Murder rate, ice cream cone sales. Let's do a factor analysis because the correlation is 0.659. It doesn't make sense to even do. That's why there has to be theory guiding this, otherwise it makes no sense. On the other hand, if I just say, well, you know what, I've got 3 variables. I want to use these 3 variables in another, I want to use these as my IV. I don't want to use all 3. Then a principal components analysis may be more meaningful here. But again, in this case, this is only for demonstration. You only have 3 variables. You're not doing a factor analysis on these 3 in most cases anyways. You're not doing a PCA on these 3 in most cases. It's just for demonstration, but you get the idea, that distinction between factor analysis and components analysis. It should be theory-based. Again, what I like to say is like 90% of what goes into your research has to be, you understanding what you want to do and what you want to show, and which technique that may help with that. Otherwise, you start letting the technique, run the show, and you're using it because you have correlation between variables. Well, that's not a justification. Or you're using it because you have multiple dependent variables. That's not a justification either. So here's the components extraction, which again, you know how to contextualize that. Okay. A little bit misleading, not in agreement with how that's written, but as long as you know what that means, you're fine. Here's where it gets really confusing, because this is done in SPSS, and what SPSS is going to report is initial eigenvalues, and then it's going to report extraction sums of squared loadings. Well, the first thing to realize is this is not really the EFA you want, right? This is not, because this is actually a components analysis. Now now what SPSS will call it is the components analysis of factor analysis. It's the components extraction of factor analysis. And what SPSS will produce for weights for the eigenvectors is not going to be exactly the same weights as you're going to get if you just did a PCA using eigenanalysis. So it's going to be a little bit different in that regard, but it's still a components analysis, no matter what we call it. Even if we call it the factor analysis or the components analysis version of factor analysis, it's still ultimately a components analysis. Now, why am I saying it's a components analysis? I'm saying it for the same reasons we talked about. Well, first of all, it says here, but again, this is the method of factor analysis called components analysis. But why am I saying components analysis dominates here? I'm saying it dominates because if I remove this component, right? I remove this component, what's going to be true about these? They're going to stay the same. And their corresponding loadings on those two components are going to stay the same. That is the important thing to realize as to what is being presented here in the output. Over here is the real EFA. Squared loadings. This is what the EFA is producing for a one-factor solution. Now, in this particular case, because it's the components analysis, we've extracted one factor. So this factor is going to be the same as this. If I extracted two, this line would just repeat itself, and this line would just repeat itself. We're extracting one component, but because it's a PCA, the extraction doesn't really mean anything, right? This does not really mean anything here because it's the same thing as what you're finding on this side, only it's just listing it in terms of one line. That changes when we look at the different version, when we look at a true factor analysis, not a principal components extraction solution, but when we look at a true factor analysis called the principal axis factoring, it's still going to produce this in terms of your components solution, but this is going to be the real EFA. And that's where this stuff is subject to change. I hope that makes sense. There's a lot to interpret there in terms of understanding what SPSS is actually producing. When you do it in R for the final exam, you're not going to run into these problems because R is not putting factor analysis and components analysis into the same bin. It's not putting into the same chapter. And in retrospect, I think it would be been better for SPSS to not put the components analysis as a version of factor analysis, because all the issues we've talked about, the uniqueness of loadings and all those things, they don't show themselves here. So that's why some of the critiques of factor analysis is also, it could be easily misused because people don't realize whether they're doing components analysis or factor analysis, but we know they're not the same. So this, for all purposes, is a components analysis. And here, we're simply keeping one component. but I didn't need to do this part. I could have just said, here, keep this component. I like how much variance is explained, keep this one. I didn't need to do this over here. When I do the principal axis factoring in a second, I will have to do this part to do the factor analysis. Okay. Here's the component. Here's the one component that, you know, we kept. Remember, we extracted. Well, we extracted, we kept it. They're using the language of extraction here because that's going to be most applicable when you do principal axis factoring or maximum likelihood factoring and other versions of factoring, factor analysis. But the PCA version, again, what I've talked about, extraction is not quite the same thing, right? Because extraction, yeah, you're keeping one. How many are you extracting? You're extracting 3. You're not extracting 1, you're extracting 3 based on the number of variables. You have 3 variables, therefore you're going to compute 3. We're going to keep 1 because it explains most of the variance. So extraction is not necessarily the best word there. It's fine when you look at it so long as you understand what we've talked about. And that's what's important, is that you understand what you're looking at. Then you say, okay, well, I know it's not extraction in the real sense of EFA. It's a PCA. Okay, I think we've said enough about that. So here's component 1. And it's got, you know, pretty high loadings on those variables. So then the challenge then becomes, I mean, you can look at your scree plot. There's the scree plot. You look at that and you say, well, there's the biggest eigenvalue. There's a lower one. Again, I said there's nothing special about the scree plot. It's not like the scree plot is like, wow, I need the scree plot to interpret this. No, you say it's got a big loading here and then smaller ones here. I could just look at the table right here. How many components exist in the data? The first one explains 75%. Again, we're doing James stuff here. This is James stuff. And I say, well, it doesn't look like these are accounting for much. It's got less than 1 eigenvalue, so maybe I'll just keep this one. And there's my interpretation. How do you interpret it? Well, it's a components analysis. So it follows the same convention of you can name the component if you want, 0.8, 0.8, 0.8. I don't know what that might mean, but you might want to try naming it. Okay, so there's another one using the two-factor. Again, two-factor orthogonal model using principal components extraction. So we know what this is about. There's our, you know, we've got what, 6 variables? And we're going to have the same idea here. If you just rotate that around, well, let's see. Where's my rotation? Page, rotate. Okay, so here's what I was talking about earlier. This is a 2-component extraction. Okay, 2-component extraction. Well, here's my original PCA. Look what happens when I keep 2. That's identical to these loadings right here. Okay, so I've just kept 2. That's not going to be the same thing when we actually do the factor analysis. And we'll talk about doing a rotation when we do the path analysis. But again, we're in the spirit of PCA here. So the initial eigenvalues, when you think about this, you're doing the principal components analysis, you're just keeping 2 components, and that's all we're doing. And again, you can look at your scree plot a little bit, but just understand that we're doing the components extraction and why that's so important to understand. You can look at those loadings there in terms of that component structure. Now the communalities are going to be this here. So we've talked a little bit about what communalities are, and here they are right here. So there's my original variables: stimulate, challenge, interest, recognize. And I'm going to take my loading for the 2-component structure, and I'm going to take this loading right here, and that's going to give me a commonality of 0.75. So the way to interpret this, and the commonalities are more relevant to when you're actually doing factor analysis and not components analysis. But you look at this, say 0.100 squared plus this one squared, and it says, well, across your factor solution, that's how much variance is explained. So if you get 1 minus the communality, then you get 0.25. So 0.25 is left unexplained here. Now it's important to look at this and to see what we're actually trying to explain. You're not really trying to explain the factors in this sense when you're looking at the communalities. You're not trying to explain the factors. What are you really trying to explain? You're trying to explain the observed variable, right? So in this spirit here, we see that this is x is equal to this idea here. X is equal to the loadings on the factors, which they've named these factors value factor and engagement factor. That's what Stevens has chosen to name them. But this is actually what you're actually doing. And that's why the communality makes some sense here in terms of saying how well does your factor solution account for this observed variable, which is accords exactly with what we see in the factor analysis model. So that's the idea there. Let's get to, let's do a real factor analysis in a second. Here's the, again, using principal components extraction. Let's get to doing a path analysis. And okay, we'll talk about the communality issue as well. I put a face there, but I'll get back to this. Now we'll get to the actual factor analysis model. So this is going to be a factor analysis doing actual factor analysis with the non-principal components method. And I want to explain this a little bit. So here it is. We have a two-factor model right here, where we have engagement is one factor, valued is another, and these are observed variables on each particular factor. And you're going to have error terms associated with that. Now, in the, and this is a correlation. This is a correlation here between factors, okay? Correlation between factors. One thing to note here, whenever you're doing a factor analysis, this here, as I may have mentioned, is entirely unknowable. Okay. These names of engagement and valued are up to you to decide what you want to name the factors. So when you're doing this analysis, engagement doesn't exist. Neither does this thing called values. You're naming these factors based on how the observed variables load onto your latent variable. So before you name these, this is F1 and this is F2. And you're coming up with a name for these things because of these loadings here. Maybe you've got 0.80, 0.70, 0.90, and you're calling this a particular name. Or maybe this loading here is 0.10, but because these two things seem to suggest that we should call it engagement, that's how you're coming up with the name. But again, how are you coming up with this name? So this is analogous to our IQ idea earlier. How are you coming up with this has nothing to do with factor analysis. What I mean by that is that when you do a factor analysis and you're reconstructing the covariance or correlation matrix, the factor analysis does not know what this is. It does not require you to name that because it's a latent variable. That's analogous to naming the component in components analysis. So just realize that whenever you hear at a research conference or in a paper when someone says, we have evidence for a two-factor IQ variable. Well, they don't have evidence for naming it IQ. What they found is a two-factor solution that provides an adequate reproduction and interpretable weights for which they believe that these things are best named engagement and value. Okay. So that's important. That's important. And that's similar to the components analysis idea, where we try to name the component. But it's even more pressing because as soon as you start doing things like this and extracting to and relating the factors, potentially relating the factors, so that you got no oblique idea here because it's not orthogonal anymore, you're relating them. That becomes, very theory laden because it's not just a transformation on data. You're kind of building a model and you have like error variances here and stuff like that, and error terms related to each observed variable. This whole model here that we're looking at can be called a structural equation model. Okay, be called the structural equation model. And when we talk about structural equation modeling more, we're going to see that you can even do things like this. You can take this error term and this one, and you might be able to relate them to one another. And we'll talk about why you might want to do that, which is very much in the spirit of SEM. But here we have a first glimpse of what a structural equation model looks like. Okay, so I just want to get onto the principle. We'll look at the assumptions later. Let's look at the principal axis factoring. That's the PATH method that I was talking about earlier. And when you're thinking about a real factor analysis, you're thinking about something like PATH, maximum likelihood, different methods of estimation that are actually not giving you the same results as you would get with the principal components analysis. So this is principal axis factoring, and this is our first, okay, I want to stress that this is our first real, what I like to call, it's a real EFA. Now we're doing real EFA. So everything before that's associated with EFA, we're still in the area of principal components analysis, really. This is where the factor analysis really takes off and where all the issues with factor analysis present themselves. Because remember earlier, we didn't have to come across all those issues that I talked about earlier. We didn't have to come across those in the earlier analysis because they were really based on a principal components analysis. So here it is. Let's look at our 4-factor anxiety model with 3 indicators per model, per factor. So these are called indicators in this context right here. Here we have a whole bunch of correlations going on between our variables. Let's look at a correlation matrix over here. So there's our initial correlation, similar to what we looked at before. Preliminary analysis, well, there's our factor analysis. Okay, so, and again, I want to stress, this is the real EFA. We are now, for the first time in the chapter, we are actually doing a real EFA. Now, when you look at this output, you can immediately see something's different here. Something's different. We're in a different area as we looked at with the PCA. What's different? Initial eigenvalues. What's initial eigenvalues really? It's a PCA. This is a PCA factor analytic solution. As I said earlier, this PCA is not going to be identical in terms of the loadings, is what you're going to get when you do it like in R or something like that. But it's still going to produce these eigenvalues. So these initial eigenvalues are based on a PCA solution, and there they are. They're in descending order, right? It makes sense. When you look at that, you go, that's not a factor. That's a component. And they're in decreasing order of magnitude, which makes sense. The first component, how many variables are subject to this analysis? I just look at this and go, there's 12. I don't even have to look at the other page because I go, there's 12. Because 12 variables are going to produce 12 components. And I look at that and I say, well, which one has the biggest eigenvalue? This one. That's the principal component, the first principal component. This is the component that accounts for most of the variance. Well, it accounts for 39% of variance in the variables. So I've got the first principal component. What's true about the second component? Uncorrelated to the first, accounting for the most variance, et cetera, et cetera, et cetera, until I've explained 100% of the variance. What's this? This is a factor analysis. This is a factor analysis. First thing you look at, go back to our previous stuff that you looked at. You say, wait a minute, in our components analysis, which Stevens is calling factor analysis, this was the same. In this particular analysis, we are keeping a 4-factor model. Now, I used the wrong word. I said keeping. I'm too used to doing components analysis because we've just done components analysis. We're not really keeping here. What are we doing? We are truly extracting. I was going to see if they use the word extracting here. They don't. We are truly extracting a factor analysis solution. Different meaning than in the PCA, even though they're used the same because they're subsuming under the same model. But extraction of a PCA solution, not the same as extraction of a factor solution. Now we enter all the stuff we talked about last time and today leading up to this. All the issues present themselves. Here's where it becomes really messy, because now you can come in and you know what this is about. Had I extracted a 2-factor solution, then what happens to this? It changes. What happens to this? It stays the same. Okay. If I'm keeping a 2-factor solution, given that I've extracted 5, then this stays the same. Right? If I do this factor analysis with, sorry, that's 4. If I do this with a 4-factor solution and I choose to keep 2, because I say it explains 51.848, that's different than if I get rid of these 2 and extract 2 factors. If I extract 2 factors, then what's going to happen is my eigenvalues are going to change, and the loadings on the factor are going to change as well. So whatever loadings I'm getting from this extraction sums of squares loadings for these 4 factors. Now, so on the next page, we're going to see F1, F2, F3, and F4, and I'm going to have all my loadings here. Whatever loadings I'm getting from this 4 solution are going to be different than if I just selected just the first 2. By selected, I'm not meaning pick these 2 out of this 4-factor selection, extraction. I mean, if I said, let me redo the analysis and get rid of these 2, these loadings are going to change. Okay, the loadings are going to change. And why? Because of the transformation idea, the non-uniqueness of the loadings. Okay, so really, really important to understand the differences between these 2 things. And SPSS doesn't really make it clear that what's going on over here. Initial, when you think of initial, you're thinking of the PCA here. But if you don't know those distinctions and you look at this and you just say, well, it's all the same, it's not all the same, because if I extracted like a 7-factor solution, then all this is going to change and my loadings are going to change. Okay, so we have to really be aware of that. The rotation sums of squared loadings, that's when I implement a rotation. And that is going to change my new eigenvalues. If you want to think of these aren't exactly eigenvalues, but you think of them as the new eigenvalues, right? So you get the initial eigenvalues, and then you're getting the new eigenvalues, and then the eigenvalues based on the rotation. Again, they're not eigenvalues. These are eigenvalues here. These are eigenvalues proper, but it doesn't hurt to think of them in terms of how the output is presented in terms of being kind of like the updated eigenvalues. But really, if you stick to calling the rotation sums of squared loadings, that's the safest way. But I mean, it's so tempting to just say, we got the new, there's total here. We got the new eigenvalues. We got the rotated eigenvalues. And that's fine as long as you know what you're looking at. Let me just, I think we're actually going to stop there and talk about this a little bit next time. Yeah, so let's stop there. We've talked a little bit about the structural equation model, and we want to talk about that as we get into next time about the confirmatory factor analysis model, which is going to be a version of factor analysis, which is also a version of structural equation modeling. So that's where we're headed. You know, so when you have like this idea that was just presented, as soon as you start doing things like this, well, it depends on what this is. I mean, if this is an exploratory analysis, then presumably you didn't know what these things were. This is F1 and this is F2. You may come around later and name these things and say, this is going to be whatever those names were, intelligence and something else. You may name them after the fact, but you didn't know what they were going in. Now, when we get into next week, we're going to develop the confirmatory factor analysis model, and it's going to look, in many cases, for that simpler case like this one, only that you're going to have a hypothesis as to the nature of those factors. So if I just go back here for just a second, and I look at this, it's actually kind of tricky to know what we're even looking at, because this could easily have been F1, F2, F3, and F4. And I run an exploratory analysis on this, and then I name these particular factors. But more to the spirit of what this actually is that if you have a hypothesis that tension is the latent variable subsuming these observed variables, then you're going to name that in a confirmatory factor analysis, and you're going to set up this model in a confirmatory factor analysis, and then you're going to evaluate the model for fit. Because what you have here in this big thing is a theory. You have a theory of what's going on. And then you're going to take that theory, and then you're going to see how well it matches up with data. And that's going to get us into the confirmatory factor analysis. Structural equation modeling, this can be seen as a basic structural equation modeling, although a structural equation modeling will often have things like this. Instead of having a two-sided correlation arrow, you may just have a one-sided arrow like this. So you may think that worry predicts this particular latent variable. So this idea of always having two-sided correlational arrows will not apply in the full structural equation modeling framework. And as I mentioned before, you may even decide to do things like this, which is to correlate these error terms, right? These unique variances, you might actually wish to correlate them. Why would you want to do that? Well, you may want to do it because maybe, you know, this first unexplained error term here is accounting for things that body type, it's unique to body type, to body 2, right? There's uniqueness associated with body 2. Well, maybe the uniqueness associated with body 2 is associated with the uniqueness associated with body 3. Now, without knowing what body 2 and body 3 are, I may have mentioned this last time, IQ in one generation, IQ in a second generation. If this is an observed variable, I'm going to have an error here and an error here. Well, I can't explain everything. You know, maybe I have some variable that's trying to explain IQ, right? Like maybe genetic transmission, explaining IQ 2, second generation. This is the parent and this is the child. So I think that as I go from IQ 1 to IQ 2, there's a predictive relationship. If your parents are smart, well, maybe the children are going to be smart too because of a genetic component. That would be the obvious thing there is that there's something genetically transmitted, and that's where a lot of these models actually came from, was trying to show that that genetic transmission across generations, related to the idea of regression and correlation and all this, where you can see why this was an important problem. Because, I mean, let me get to the point, is people like Galton and Pearson had this idea of selective breeding with people. Because if traits were genetically transferred, then maybe you can actually speed up the in their eyes, the improvement of the species. Because if smart parents are more likely to have smart kids and you want to produce the smartest society you could, then this is where that regression idea came from in terms of accounting for that transfer of information genetically. Right? A lot of correlation and regression came from eugenics motivations, which have now been dropped, of course, because they have horrible, awful social consequences, and there's a whole bunch of issues involved. But that's where a lot of the historical impetus for these tools actually comes from, which is very, very interesting from a historical point of view. When you look at this historically, you actually see, what motivated people to come up with regression correlation, and not all the motivation were admirable. So getting back to the point here, if IQ1 predicts IQ2, and we infer there's a genetic component, well, this is everything that doesn't predict, right? So everything unaccounted for by X is ending up in the error term. Everything that doesn't account for this IQ prediction is ending up in the error term. Maybe everything that's not accounted for here and not accounted for here is related. What could it be? If this is a genetic transmission, maybe I can explain this through genetic transmission. Well, maybe I have environment, the nature-nurture debate type of thing. So I can't just go by this relation. The unexplained variation is actually important. And this here is unobserved, this is unobserved, and this is unobserved. So these are latent variables, errors. That's why we said when we talk about regression into these types of models, I said, no longer are we going to think of the error term as just an error term. A plus bx plus e. We're no longer going to think of this as just, it's just error, it's just unexplained variation. Well, it's unexplained variation, but there could be things in that unexplained variation. Right? Maybe there's something in here. Maybe there's multiple things. Maybe there's true chance. Maybe there's measurement error. Maybe there's random shocks. But maybe there's something really, really interesting. Maybe it's environment that's actually in there, at least in part. Well, how could you assess it? Get the correlation, see if they're related. Now, it's not going to tell you if it's environment, but it might hint at it. Say, if you have a theory, right, you say, well, this is based on genetic. Everything else, maybe it's based on the environment. And right away, you get that nature-nurture idea. So maybe the same thing is happening here, maybe not, but you get these ideas of why you would potentially want to correlate error terms, and the expansion of the error term into a more theoretically rich concept. And if you talk to structural equation modelers, the people who they do structural equation models all day, and they publish in structural equation models every day and everything like that, these error terms become it's kind of like a fascination thing as to what's contained in the error term. If you talk to a regression, someone who does regressions all day, well, they don't look at the error terms like that. They just look at it as unexplained variation. Factor analysis, one nice thing about factor analysis really forces you to think about what's in there. What might be in there? You know what's in here because this is explaining why, but what's in here? Last point for today, you may remember from ANOVA models, when you do like random effects and stuff like that, and you get the MS error, well, the question of what's in MS error could be very theoretically meaningful. Maybe you've got your treatment effect here, your treatment effect, but you've got a lot of stuff that ends up being in the error term. What's the error term? Interesting. From a research perspective, it's not simply partitioning variability in the ANOVA, it's asking, what does that error term contain? That is an analogous concept of asking, what does that error term contain? Okay, so what we've done today is we've looked at the exploratory factor analysis model. We're into confirmatory factor analysis, which we're going to finish up next time. And that's going to be a version of structural equation modeling. So we're going to continue here next week, finish this up in the first half of next week's lecture. And then we're going to be into cluster analysis, which will get us back into the James text. Okay, so that's it for this week. We will see you next time.